Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Eirini Katsidoniotak. She will be giving a talk on the application of multi-fidelity modeling based on nonlinear autoregressive Gaussian process regression for the prediction of structural dynamics. Eirini Katsidoniotak is a postdoctoral fellow at the Stochastic Analysis and Nonlinear Dynamics Lab in the Department of Mechanical Engineering at MIT. Her research focuses on developing reduced order models using machine learning and statistical methods to predict extreme events and quantify uncertainty in complex multidimensional ocean engineering systems. She completed her PhD in computational engineering at Uppsala University, Sweden in 2023, where she developed and validated CFD models to simulate offshore floating structures interacting with extreme ocean waves. With that short introduction, the floor is yours and you can start your presentation.
Thank you so much for the nice introduction. And also I'd like to thank Professor Karniadakis and the seminar organizers for the opportunity to present my latest research. So in this seminar, I'll discuss a real-world application where I've developed a multi-fidelity framework to predict the structural dynamics of systems deployed in marine environments. So the application focuses on marine aquaculture, which is a growing sector that offers a sustainable solution for food production. As the aquaculture industry expands, it faces significant challenges due to the harsh marine environment and high operational costs. So these factors create a strong demand for novel technologies that facilitate remote management and enable autonomous operations in fish farms. So digital twin technology can significantly advance aquaculture by combining real-time data from on-site monitoring equipment with realistic models within a digital twin framework. We can get more accurate insights into the dynamics of fish farms. And here, machine learning and the surrogate models that we can develop with machine learning is essential, as it helps to create the necessary map between marine conditions and the dynamic responses of the fish cages. However, high quality and comprehensive data, which is typically needed to predict real-world behavior, can be challenging or expensive to obtain. And given these challenges, several key questions arise when developing models for a digital twin framework. For example, how can we develop predictive models that integrate and learn from diverse sources of information? How can we address the scarcity of real observational data? Or how can we ensure that the predictions closely align with the actual system response? So in fish farms, there is a variety of data sources available, each with different level of fidelity. For example, we have model scale experiments, which are conducted in a controlled environment and with gathered precise measurements of structural dynamics. Also, we have full-scale measuring campaigns to collect data under actual marine conditions, but this is something very costly and complex. Also, high-fidelity simulations offer realistic insights at the expense of computational cost, and lower fidelity simulations that provide quicker, more accessible information, but with less detail. So together, these diverse data sources can contribute to a comprehensive understanding of the fish farm dynamics. So now, in this case, multi-fidelity modeling can be very useful, since when we have different data sources or levels of accuracy. So basically, in multi-fidelity modeling, we combine cheaper, less accurate, low-fidelity data with a limited amount of high-fidelity observations in order to train machine learning models that they are able to uncover cross correlations between variables and improve predictive accuracy. For example, in this context, let's say we have a small number of experimental measurements, which are very difficult and costly to obtain, with synthetic data generated from a fast and cheap computational model. So among the existing methods in multi-fidelity modeling, the Gaussian process has drawn much attention in a wide range of applications. So before talking about how multi-fidelity modeling is implemented in our application, let's briefly talk about the theory of multi-fidelity modeling using Gaussian processes. So let's start with a simple example. To illustrate how a linear multi-fidelity model operates, let's consider two fidelity functions as shown in this left plot here. So the blue curve represents the low fidelity solution, and the red is the high fidelity solution. And we sample 12 points from the low fidelity, and just we get 6 samples from the high fidelity solution. And now, if we apply the linear multi-fidelity GP, the middle plot shows the prediction of multi-fidelity GP, which is this dashed yellow line. And in this case, the model is able to learn the relationship between the low and high fidelity observations, and the posterior mean of the GP now closely aligned with the true high fidelity function. And also the associated uncertainty of this prediction is relatively small given the good fit. So what if we don't follow this multi-fidelity framework and we just try to train a standard GP using these few high fidelity samples? So in this case, given that we train a standard GP model, as you can see on the right, on this right plot, the prediction leads to much higher uncertainty, and compared to the case that we have this linear multi-fidelity framework. Okay, so let's talk a bit about the basic maths behind this linear multi-fidelity scheme. So going back to the paper from Kennedy and O'Hagan, in multi-fidelity modeling, we construct models where the high fidelity output is a function of the low fidelity plus an error function. So the fidelity levels are connected each other through this linear autoregressive scheme, and that can be generalized. Let's say if we have S levels of fidelity, that can generalize using this formula, which practically says that the higher level of fidelity Ft is expressed as a linear relationship with the data from the lower fidelity Ft minus 1 multiplied by this cross-correlation factor, rho, and the discrepancy term delta T of x. And also, we note here that the Ft minus 1, delta T, and Ft are all modeled as Gaussian processes. And for the sake of clarity of this presentation, let's focus only on 2 levels of fidelity. However, the method is generalized to multiple levels. So let's say we have this low fidelity x1, y1, where x1 is a matrix with n1 is the number of available low fidelity data, and d is the input dimensionality. And x2, y2 is the high fidelity level data with n2 is the number of high fidelity data which is smaller than n1. So now these low and high fidelity data are expressed as a single Gaussian process with a prior mean equal to 0 And the joint covariance, the K matrix, is this 4 block here, where each part of the block expresses the correlations between data. In order to train this model, we maximize the marginal log likelihood function, the one written here. However, something to note in this case is that if the K is has size n by n, and n is the sum of n1 and n2. So in the case that we have large data set, this K has great memory requirement, and the inversion has a computational complexity. So this approach for large data set is prohibitive due to these computational constraints of the covariance. So what we do in this case to address this issue, this recursive autoregressive scheme, as suggested by Regression, can be a solution here. And in this case, we replace this ft minus 1, the GP prior, with a GP posterior f asterisk t minus 1 from the previous inference level, while at the same time we assume this nested structure in the data, which means that the training inputs of the higher fidelity needs to be a subset of the training inputs of the lower fidelity. And according to Regression, this scheme is exactly matching the Gaussian posterior distribution, which is predicted by the fully coupled scheme from Kennedy and O'Hagan. But now in this case, we have to solve S standard Gaussian process regression problems. So now the inference problem is decoupled into S standard GPs. And now the prediction. So the posterior of the high fidelity level is taken as the prediction of the multi-fidelity model with a predictive mean and variance given by these formulas. So this is the linear multi-fidelity. And in this case, we consider that between the high and low fidelity, we have linear correlation. But what happens in case that these two levels of fidelity, they don't have linear correlation? For example, look at these functions here in this left plot. In this case, we implement the nonlinear multi-fidelity GP. And I'll start by showing you what happens if in this nonlinear case, if we still implement a linear multi-fidelity GP. The posterior of the high-level GP, you see that fails, cannot match the true solution. However, if we apply this multi-fidelity scheme, which I'm going to describe you later, we see how well at the end the prediction managed to fit the true solution. And so we see a significant improvement of the solution compared to the linear model. So what happens actually here? So we start from this linear autoregressive scheme, and then replace this correlation factor rho with a non-deterministic function. And this results to a model that we can capture actually the nonlinear relationship between the fidelities. So instead of rho, we consider this ZT minus 1, which is a GP prior. And then actually the model at level T is a nested composition of two functions plus the discrepancy term. And both functions are GP priors. And this gives actually rise to the so-called GP deep Gaussian processes. And this introduces non-Gaussian behavior for the posterior. And in this case, this formula allows the construction of nonlinear multi-fidelity fusion algorithms. However, in order to solve these deep Gaussian processes, leads to increased computational cost and complexity due to the non-Gaussian posteriors. And this difficulty is what motivates then the next step, which is the recursive scheme, again motivated by Legrathier, replacing the ft-1 prior with the posterior of the previous inference level. So in this case, we get a nonlinear autoregressive scheme, and this GT follows a Gaussian distribution. However, now, as you see, we have this scheme maps the input space, the X, and the outputs of the lower fidelity with the output of the higher fidelity model. So we need to construct a kernel that considers the fact that f asterisk t minus 1 and x belong to different spaces. And this is how it comes this covariance function of GT. And in order to train this nonlinear multi-fidelity GP, the first level is simple, is a standard GP that we try to maximize the likelihood using a standard kernel. But then for the next fidelities, we have this data set here. Again, we try to maximize the likelihood, but using this kernel. And in this case, we have to estimate 2 times the dimensionality plus 3, which are the hyperparameters. And this is explained because now the kernels account for the directional anisotropy at each input direction using these automatic relevance determination weights, which actually this ARD brings highly relevant input features to estimate to enhance the prediction accuracy. So basically, we weight the importance of the inputs in this case. And now, when it comes to prediction, for the high level of fidelity, we have to perform predictions considering the uncertainty of the inputs from the previous fidelity level. So in this case, we compute the predictive posterior mean and variance at every new point x asterisk by Monte Carlo integration of this equation in order to propagate the uncertainty from the previous level of prediction. So yeah, this requires at each level of fidelity to sample the posteriors and propagate the output as an input to the next inference level. Okay, so let's see now how all these apply in a real application. So as I mentioned, the application here is about marine aquaculture. And the goal is to develop a digital twin for remote monitoring of fish farms. That means that an operator, like this guy here, is able to know the dynamic behavior of the fish cages in real time in order to evaluate the structural integrity, also to enable autonomous operations in fish farms like net cleaning, net inspection, and other. So let's see how this multi-fidelity modeling can be applied in this context. And in this case, the data that we have available are numerical simulation data and also real measurements from sensors.
Eirini, sorry to interrupt you. Can you say how many sensors are there?
Yeah, I'm gonna show this in the next, one of the next, yeah. So in this case, I'm gonna use this nonlinear multi-fidelity GP in order to capture the nonlinearities that we have in nonlinear, in real world data. And actually this multi-fidelity nonlinear framework has been validated successfully in benchmark problems, but now its performance is explored in a real application. So now I'm gonna say about the data. First of all the data we have in this study are obtained from the fish farm at Sintef, which is a full-scale laboratory facility in Norway. So all relevant data are used in this study corresponds to this fish farm. And first, yeah, the low fidelity data are from numerical simulations. The FHSIM software actually is a software that simulates real-world data with focus on marine applications. This video is from FHSIM, and actually FHSIM solves the nonlinear systems formulated as ordinary differential equations using time domain integration. So we have 1,000 simulations. We evaluated 1,000 scenarios covering a broad spectrum of marine conditions. Each simulation takes approximately 20 minutes. And FHSIM provides a good approximation of the system dynamics. However, is not able to capture the exact realistic behavior of the gauge. So now the high fidelity data are from sensors. You see at these sketches here, the position of the sketch of the sensors. So first of all, the period of measurement is a bit less than 2 months from January 18th to March 5th in 2020. There is this buoy here that is equipped with sensors and measures all the incoming conditions like wave, ocean currents. Then we have 5 sensors located at these red points. They measure the mooring lines, the mooring line loads. The mooring lines are the components that keep this cage in place. And also we have 3 sensors located at these 3 different positions, and they measure the displacement of the cage at the positions where the sensor is located. So we see how the cage is moving at this point, at this point, and at this point. So all the data were collected using a wireless sensor network. And yeah, this period is winter, so it's a relatively harsh period of the year. So yeah, we expect interesting thing to happen there.
One more question.
Yeah.
How about sensors for wind, data from winds, because this is exposed to the wind, right?
Mm-hmm.
Surface waves, of course, may dominate, but you still have wind forces.
Yes, we don't have the wind measurements here because it's more about the interaction with the sea. And actually, what we notice here is that the ocean current is more important in terms of the dynamic compared to the waves. So the ocean currents give, let's say, the displacement or the initial shape, and then the wave creates small oscillations around this shape. But the ocean current is what provides the main, let's say, displacement or deformation here. So basically, yeah, we are more interested about what happens with the currents. And yeah, okay. We don't know winds at all. We don't have these measurements. Okay, and the framework now, this multi-fidelity framework, how it works. We have these measurements from the buoy. As I said, we focus mainly on the current, the direction, and the speed. We give this current to the low fidelity level. And then we get the prediction regarding the mooring load and the deformation. And then we give this low fidelity prediction together with the ocean current to the high fidelity level GP to take the output, the final prediction. So yeah, and this workflow actually is completed in a few seconds due to the algorithmic simplicity and low computational cost of this multi-fidelity method. Okay, and now
sorry again.
Yeah.
Can you explain? So the input is the current.
Yes.
And then where do the displacement, the dynamics should go into a high fidelity directly? Is that what you denote there with the low? Yeah, I see depth sensor. Yeah, so the lower part here provides information to node vertical displacement. That's experimental data, right?
Yeah. So from the low fidelity, we manage, and I will show you how, we get the whole deformation. And then we select the nodes of interest or the locations of interest, and we extract the displacement for these locations. And we give actually the location, the displacement for few points as input to the high fidelity.
So it's not just only the measurements. There are also other nodes that you include, the dynamics, because you only have a few, 3, 4 sensors.
Yes, we have, I know where are the positions of these sensors. So I extract the displacement at the position of this cage where the sensors, the positions that corresponds to the sensors.
Okay, so the input there is four signals.
3, yeah, we build the model to predict for these 3 positions the displacement.
Right, 3 displacements.
Yeah.
Okay.
But at this first level, we build this model to find the whole deformation of the cage, because maybe in a later stage, someone wants to add more sensors, maybe in another experiment in the future, or to have more sensors or different locations. So in this case, we retrain this part of the framework. So this low fidelity model actually is able to substitute the numerical simulations. And we train and trust this low fidelity component. And then if in the future get more sensor measurements or whatever, then we focus to retrain this high fidelity part.
Okay, thank you.
And okay, now how it works. Let's talk about how to build the low fidelity GP. So, okay, to build the component, the GP actually that predicts the mooring load is a straightforward process. So we give the currents as input, the mooring loads as output, and we build this GP. The dimensionality of these mooring loads is low, so we can easily build a model to predict the mooring loads. But when it comes to the net deformation, so the net is a very flexible structure. And for the purposes of the numerical simulation, this net structure inside the FHSIM software is modeled as a collection of triangular elements which are interconnected through nodes. So in our cases, the cage is discretized in 321 nodes. And for each node, we get the XYZ displacement. So at the end, we have 963 dataset that describe the deformation of this cage. So this is a large dataset, especially when we want to build a GP. So that's why we have to do dimensionality reduction here. So what we do, okay, is a standard principal component analysis. So we put all data that describe the XYZ for all the nodes in this matrix and for all the 1,000 scenarios that we examined. standardize the data, find covariance, then do the eigenanalysis to find eigenvectors, eigenvalues. We sort the eigenvalues in order to find, the directions with the largest variance. In our case, I'll show you why we choose just three components. And then when we project the data in these directions, we get the three principal component coefficients. And so basically from this data matrix, we end up having this smaller matrix with three coefficients. And then when someone knows these three coefficients, can go back and reconstruct the data by multiplying with the eigenvectors. So in our case, we decided to keep 93% of the cumulative variance, and that gives three coefficients. And when we reconstruct the cage using the three coefficients, we get the shape of the cage, which is actually very good if we compare with the actual cage that is estimated by the numerical model. And yeah, now we build this Gaussian process regarding the net deformation prediction that maps the ocean current with the PCA coefficients. And then when we know the PCA coefficients, we go back, we do the reconstruction to get the shape deformation. And this is what I explain also here in the data. And yeah, to show you the accuracy of this GP for predicting the PCA coefficients, these are on test data. So we haven't trained the model using those data. So we see from the scatter plots and the R-square that the prediction is very, very good. And yeah, when we reconstruct the cage using the predicted PCA for three different environmental conditions, we can get very good reconstruction compared to the actual shape. And this actually, all this process is a very, very fast process in terms of computational cost. Similar about the mooring loads, the low fidelity GP maps the current with the loads. And again, we have very good prediction accuracy. And in this case, we consider that we have developed a low fidelity GP that has very good accuracy and is able to substitute the numerical simulations. So as I said, each simulation at FHSIM takes 20 minutes to calculate one marine condition, whereas with these models, in a few seconds, we can estimate too many different conditions. And yeah, if we go back again to the workflow, I talk about this part of the workflow. So now let's see how we do it in order to build the high fidelity model. So now we have all these measurements for the almost 2 months period. So we have the measurements from the currents. So we give these measurements to the low fidelity GP, and we get the low fidelity predictions. And regarding the displacement from the deformation, we extract the displacement that corresponds to the three positions where the sensors are placed. By the way, I want to say here that for this for the load shackles, the ones that they measure the mooring loads, there was loss of data during the measurement period. So for the depth sensors and the currents, we have this almost 2-month period of measurement. However, for the forces in the mooring lines, we end up having only 36 hours. Yeah, here I remind how the depth sensors are placed. in order to understand at the end what is the data that has this block of the data set. Okay, now let's see how we train the high fidelity component. Okay, so as I mentioned, we give all these measurements and we find the low fidelity predictions. And actually here, you can see how the low fidelity prediction looks like for the depth sensor, one of the depth sensors, and for the load sensors. So the low fidelity prediction gives some kind of trend, but of course deviates significantly from the reality. So the idea now for training the multi-fidelity GP, the high fidelity GP, is to use just a few data. We don't want to use all the data, just to show how this multi-fidelity model works. The idea is to use just a few of the available data. So,
but the available data is, I see it's a very high frequency, right? Is it every 10 minutes or?
Yeah, every few minutes we have data.
Yeah.
So we choose just these red dots, and actually we use use the data that corresponds to the red dots from the low fidelity prediction and from the currents. And we give this as, the inputs and the outputs to train the model. And yeah, now regarding the prediction accuracy, I show these scatter plots here where we see what the low fidelity part predicts. For the three sensors, we see that the prediction is not so good. However, we see how the high fidelity part corrects the solution and brings the measurements closer to, to the linear relationship. Of course, we still have some deviations because, as you saw, the data are very, the trend is very non-linear, I would say, or so we cannot definitely capture some parts of the measurements. So you can see maybe better here, like that this is the multi-fidelity prediction that comes much closer, but for sure we cannot capture all the trend exactly, but is of course a very big improvement compared to what the low fidelity component initially gives. And so similar for the mooring loads, now we get a bit even better trend when it comes to high fidelity. So we see how the low fidelity prediction for the three cases here is very, very bad, and then how, is improved using this high fidelity part. And same visualization for the loads in the mooring lines. We see the correction from the low fidelity. The high fidelity solution comes much closer to the measurements. Okay, so that was basically the part for the multi-fidelity modeling and the outputs we get from the model. I want also to show you something that is a bit different, but that was something that inspired me during this project, because I understand how important is the prediction of these flexible net cages, like their shape is very important for fish farm applications. It's important to know how the cage is deformed, when it interacts with the ocean currents. And surrogate models can provide very good and fast insights regarding this shape. So yeah, developing surrogate models for predicting flexible structural deformation is a novel application. And the net cages have this graph structure they are graph structure data. And this gives me the motivation to implement the graph convolutional neural networks to predict the deformations. And the graph neural network actually receives the node features and their connection and can predict the deformation, the displacement at each node. So for example, important inputs that we give to the graph neural network is this edge feature matrix, which is called the adjacency matrix, which says, for example, that node 1 is connected with node 2. That's why we have 1 here, but it's not connected with 3 or 4. So it shows how the nodes are connected. And also we give the node features where we say at each node, what are the inputs? For example, at each node, we give the initial, the coordinates at rest for each node, and also the ocean current conditions. And then in this case, in order for the message aggregation and update part, I follow the methodology that is described by Kip. So basically, I have 2 layers here, and the graph convolution takes the adjacency matrix and the node features from the previous layer and outputs the node features for the next layer. And this is actually described by this formula, this trend. And another interesting thing here, because initially I used several activation functions, but I found that the Swish activation function is the one that gives the better result. And I can explain that because this activation function has a better ability to introduce non-linearities in this graph structure data. And also during the training, I use a custom loss function where I assign weights to the nodes. So in the nodes that they are in the lower layers of the net cage, the lower layers have more deformation. So in these nodes, the weights are higher with the maximum weight in this bottom node, which has the maximum, deformation, let's say, can move around anywhere. And yeah, it gives very, very good prediction accuracy, this model, when we compare with the actual deformation. And also I compared this graph neural network structure with the prediction I got previously from the Gaussian process with the dimension reduction. There is, it has slightly better prediction accuracy. And I believe that part of the reason is because when we do the Gaussian process model, we took before this dimensional reduction step, and this maybe introduces some extra error, which reflects on the prediction accuracy. So yeah, that was all. So some key takeaways out of this seminar today is that this nonlinear multi-fidelity GP has been before tested in benchmark problems, but today I show you how it works for a real world application when it comes to real data. And it shows very good performance, and the predictions, they are very close to the reality. Also, another interesting point is that I show how to develop surrogate models for these flexible structures as the net cages. And also that the graph convolutional networks can work for structural deformation problems, because so far we mainly see graph neural networks for applications like drug discovery or biology, but it's interesting to see them in structural problems. And as future work, of course, I'd like to have more high fidelity data to cover maybe the entire year instead of just 2 months. Also, I'd like to generalize this multi-fidelity framework to predict, to add more quantities of interest, like fish behavior or environmental conditions in fish farms. And in order to do that, we need multi-fidelity models that support higher dimensionality. So probably multi-fidelity neural networks can work for this expansion, let's say. So yeah, before I close, I'd like to acknowledge our collaboration with SINTEF. They gave us access to all the data. And yeah, and also they provided guidance regarding the data and what are the needs of the industry. And also I'd like to acknowledge the source of funding. And yeah, thank you so much for.
Thank you so much, Eirini, for your great talk. Now we open the floor for questions. Do we have any questions from the audience for the speaker?
Hi, Eirini. I have a question. This is Nikhil. I'm a PhD student working with Professor Karnidakis. I was just, it was a really great talk. I was just wondering, have you compare with, like, have you did any like ablation study or something, like how the amount of low fidelity data really helps you to learn your case for the high fidelity case, like impact of accuracy in the multi-fidelity approximation when you vary the low fidelity data? Have you explored that?
So the thanks for your question. So the low fidelity data, actually, we have them covering, let's say, marine conditions for a bigger, like we had ocean currents that they start, let's say, from 0 to 4 meters per cent. So they cover a very big range of marine conditions, I mean, ocean current speed. And then we were sure that we created a very accurate low fidelity model for this range of conditions. And then we chose, I mean, our higher fidelity data cover a smaller range of input conditions, which is actually part of this bigger range of the higher, of the initial first level of inputs.
Okay, I see. So in this case, like your dynamics is limited to a smaller case in the case of high fidelity data, if I understood right.
So yeah, the high fidelity data were a sub space of the low fidelity.
Okay. Yeah. Great. I think we also did like similar exploration in our case, but with the idea of using neural networks to identify the cross correlation between the low fidelity data and high fidelity data. And so what we actually tried to do was, like, we were combining the FE simulations data with the real imaging data from the clinic. And we found, like, neural networks, it was really nice to identify the cross correlation, and we got really good accuracy in that case. Maybe I'll share you the paper in the chat. Yeah. We have it on archive. You can take a look at that.
Yeah, now you mentioned archive. Also, this work is in archive, so in case someone is interested. But yeah, I'll be very interested to see your work.
Sure. Thank you.
Thank you. So, do we have any questions for the speaker? I saw Mario turn on his microphone. Yes.
Hi, thank you, Eirini, for the presentation. I have a question about the sampling data. I saw that like a small subset of samples.
Maria, can you introduce yourself? Who are you?
Yes, hi, I am Eirini's sister. And actually,
I didn't expect my sister to ask questions.
It's the first time I see this project, so the question is real. I saw like that you get the subset of sample data. Can you use maybe some sort of uncertainty of your outcome to evaluate the number of samples you got from high fidelity data instead of just getting like a random number of samples?
So I'm not sure if I understand. So you mean in this You mean here?
Yes, here. I see like that you got the high fidelity data randomly sampled from the black line there. So my question is, maybe you can use your output's uncertainty to evaluate the number of red dots. So maybe you can see as the uncertainty of your output maybe converges. This is a way to say, maybe yes, instead of 10 points here, maybe you can use 12 points or more.
I see. I mean, the idea was like to choose the training data in a way that someone blindly would pick, like if someone has access only to 20 or 30 data, that you cannot control the way that you obtain them. Because in this case, okay, we had data covering 2 months, but maybe in some other cases, someone is able to have only 100 data, or so you can't really control what are the data that someone gives you. So that's why I randomly pick those data. Because it's not always, the user doesn't have access to control what are the data from a real world experiment someone can expect to have, or yeah, it's something that is randomly generated.
Okay, that makes sense. Thank you.
But I think what Maria is suggesting is maybe building a acquisition function, and then based on that you can move sensors or how often you go to your sensors and things like that. But I have another suggestion. So in these systems, and you try to build a digital twin or physical twin, you have a lot of historical data because it's and throughout the year different conditions. So you can actually approach this from the meta learning point of view. So you can introduce maybe a functional prior. So it's a Bayesian framework, but it's a functional prior which will give you from historical data the most informative. And you can do also multi-fidelity here, but you can have the most informative prior. And then as you acquire data, even a couple of points are enough to calibrate the posterior. So I see Zogren here. He put on the chat another paper for you. But this is how I would build this. So basically, right now you're only looking at data, new data, but you don't take into account the fact that this structure has been there for years and it has undergone all sorts of loads. So all that is in your database. So there's a way to capture that through a functional prior. So instead of a ad hoc prior, you use a prior that you learn using, in our paper, we did GANs, for example, and historical data to have a smooth prior, but you can use normalizing flows, you can use diffusion models. So Gen AI plus historical data gives you the most informative prior. If you have a most informative prior, then the posterior is just a few points away from actually calibrating it. So this would be something permanent, which I would call a digital twin. But think about foundation models, right? That's sort of if this structure changes all the time, and but basically the same structure. Of course, it is aging, that it's fouling, accumulating, and the conditions change, but they're seasonal. So that's why. Zogren, did you want to add anything to this? Because I saw you get excited.
Right. I think your comments are valid. Yeah, I just put the link to the totem prior to the chat, so you can take a look at it. Yes. So we use historical data to train a generative models, then normalized flow, whatever it is, and then we use that as a informative prior. And so with very few data points, we are able to make really great accurate prediction and with uncertainty. So I think this is very good suggestion. Yes.
Yeah, actually that's very interesting. So in this case, let's say that someone has data, even in this case that I have only 2 months period. So how do I do that if I have just for this limited 2 months and not for many years? That would work in this framework?
Yeah, as long as the prior doesn't really change along the time. So you can always like update your function prior when new data coming in. I mean, that's a different story. But like the paper I just sent you in the chat only consider like one shot posterior. Oh no, sorry, one shot prior learning. Yeah. So what you're asking is what happens if we have more and more data? How do we update the prior? Is that what you're asking?
I mean,
Yeah, that would be. I think that would be one of the like future work. I haven't seen anyone done this before.
No. I think Eirini is asking because she has a very limited, only a 2-month span. I mean, you can demonstrate the framework for that span.
Oh,
Yeah. So because seasonal variations are very important in the North Sea there. So you have to capture that. So seasonality should be part of your envelope.
prior information. Yes.
The prior, yeah, to be robust for all seasons. But for within that framework that you have, basically what we're saying, you can use the same data and reformulate the problem as an extension of Bayesian framework, which is these functional priors. Because Bayesian framework, you have ad hoc priors. Here you want to have informative priors, which do not require a lot of data for a new event. And one of the things that you will see in the paper is that you can actually extrapolate. The only way to extrapolate is using meta-learning methods.
I see.
Meta-learning is you're sort of learning to learn, right? So you can extrapolate, unlike machine learning that you cannot extrapolate.
Okay, that's very interesting. I'll see this how I can implement even using the same data. I mean, even without adding.
Right.
Good.
Okay, do we have any more questions for the speaker?
Maybe Alan, do you have any comments about the GCN for the cage, for the fish cage?
No, it looked very interesting, like to see GCN applied for structural deformation.
Yeah.
Yeah. So, like, what exactly are you predicting there? Are you predicting the evolution in time or predicting the initial to final mapping?
Sorry.
So, like, are you predicting the evolution in time or are you predicting the?
No. Actually, is for each condition, like for each input, we look for the average shape. So we don't see how we don't capture like small oscillations over the time. So it's the average shape for each, let's say, incoming ocean current.
All right. Okay.
Yeah.
But in principle, you could evolve the dynamics.
Mm-hmm.
That's why I asked Alan, because he's working on that. He just released a paper on evolving graphs. Actually, no, you haven't released yet, right? The Mamba G2G.
Oh, no, it's not done. We haven't released it.
Okay.
Yeah, that is actually, I don't know about the computational complexity of training, something to do, the whole during over a time period. I guess the computational complexity would be because to train these models, I mean, takes some time, even in the case that they predict the average. So in order to train it to do the whole movement over a specific period of time, I guess that has a high computational cost for training, right?
Yeah, maybe, yeah, that's true.
But do you know the code that uses GCNs for fluids from DeepMind?
Okay.
It's an open source code. If you can do fluids using GCN, I'm sure you can do a structure like the cage. and because you have the bonds and so in fluids the particles are moving and you don't have control of the so that graph continuously changes. Here your graph changes, but it's topologically the same. There's no folds, there's nothing. And so I think there's some thing you can learn, but they use GCN plus. I'm not sure what is their method. Alan, do you know is the method to evolve the?
So they use like GCNs, like they have a processor, they have an encoder, processor, decoder configuration. So in the processor, they use GCNs. So they're like doing fluid particle simulations. There is another related paper which would be more interesting. I'll put it in the chat. What they're doing is like learning the evolution of a cloth or some kind of a geometry, like some kind of a deformation of a cloth or something like that. Like you can like.
Oh yeah, the clothes. They have the clothes. Yes.
Yeah.
That's right. Yes. So that would be very similar to what it is. Yeah.
I mean,
That's a good start.
I mean, that's very interesting feedback so far for both applications.
Okay.
Yeah,
No
thank you.
more comments, question? I think there is no more questions.
Hi, Nazir.
Yes.
I don't have comments. I have a structure to show. Can I share my screen?
Yeah. I stopped sharing mine.
Yep. Is it visible? These are some net structure, architectural structures.
No, we see your calendar.
Yeah,
Oh,
it's on the other screen, right? On the you can stop sharing and
now it's visible.
share.
Yes.
No, but it's the browser, right?
Yeah, in browser.
Yes.
Sorry. Some net structure is visible now. Let me stop sharing.
Yeah, it's fine. That's what you want to show, that all these floating structures.
Yeah, floating structure. These are designed long back by some architect. So these are some net structure.
Now we don't see it, but you can put the website on the chat and people will look at it. Okay. Yeah, we get it.
Yeah.
So I think we don't have any more questions or comments. Kamal, do you want to explain anything? Because your
No,
microphone
these are
is...
some, when I was looking at the presentation, I remember this old video from YouTube where they designed some architectural structure using net, fishnet basically.
What happened to our speaker? Okay, if nobody has any more questions, so I think it's time to close the session. Thank you, Eirini, for your great talk and for your time. And thank you, everybody, for joining us today. I hope everybody has a great weekend ahead, and bye.
Thank you so much. Bye.